What we have talked about vector spaces so far seem not so related to the first 6 chapters, but here we have come to the connection. Subspaces. A subset W of a vector space is called a subspace of V if the zero vector of V is in W and the sum is in W whenever U, V are in W, and scale multiple of U is in W whenever U is in W, and for all scalar C. So here we also have subspaces, but now subspaces are no longer limited to a subset of Rn. Instead, we have subspaces of a vector space. The question, is the zero vector, is the set of only the zero vector a subspace of V? That's indeed the case, right? Like we had seen earlier for subspace of Rn. But this is a trivial subspace. A subspace other than this is simple subspace is called a non-zero subspace. Having subspaces of a vector space turns out to be a very convenient thing. Because of this result, if W is a subspace of a vector space, V is known to be in vector space already, then W is a vector space. Remember when we define vector space, it has to satisfy, it's a set, it has 2 operations, and those 2 operations have to satisfy the 8 axioms of a vector space. But now, if we already have a subspace, we can easily obtain all the subspace by simply showing that W is a subspace of V. For example, consider V C infinity. C infinity is the subset of the function space Fr consisting of functions that have derivatives of all orders. So whenever a function is in the set C infinity, if the nth derivative of f exists for every positive n, so f has nth derivative for all positive n. Fr is already known to be a vector space. So if we want to show that this is C infinity is a subspace, is a vector space, all that we need to do is to show that C infinity is a subspace of f of R, and then showing that this is a subspace of Fr is usually much easier to do than going from scratch to show that C infinity is a vector space. And you can verify that indeed C infinity is a subspace of f of R. So it is a vector space. Like Rn, we have linear combinations and span for vectors in vector space. S is a subset of a vector space V, and S is possibly infinite. There may be infinitely many number of vectors in S, and a vector in V is a linear combination of the vectors in S. If we have V1 to Vk in S and some scalars C1 to Ck, such that V is a linear combination of these V vectors, and these Ci, like before, we call them linear combination coefficients. For example, let's consider M 2 by 2, and let's consider the set F. It has 4 vectors. Of course, the vectors in M2 by 2 are matrices. So we have 4 matrices, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Question: is this matrix a linear combination of the vectors in S? And we can linearly combine these vectors to get this vector, right? We call this vector, but it's actually a matrix. Okay, what would be the linear combination coefficient? We have a 2 here, so let's put down 2, and then there's a 1, 3 here, so let's put 3 here, and a 1, and then a 0, then we get this vector on the left hand side. Now let's consider another example, P3. P3 is, remember, it's the vector space, and it contains polynomial of degree less or equal to 3. And S1 is a subset of P3. It has 4 vectors, 1x, x squared, x3, x raised to the power of 3. Is this polynomial a linear combination of the vectors in S? Let's try this. If x is, we can write it as 2 times 1, and then 3 times x, and 1 times x squared. So that's it. It's indeed a linear combination of the vectors in S1. Now span. The definition of span is very much like before. The span of a non-empty subset S of a vector space V is the set of all linear combinations of vectors in S. The set is denoted by span S. For example, let's consider the span of these 4 vectors that we have seen earlier. This is a subset of M2 by 2. What would be the span of this set? If we consider arbitrary linear combination over these 4 vectors, then we would get arbitrary 2 by 2 matrices, right? So that would be the same as M2 by 2. How about the span of these 4 polynomials? What would we get? If we consider arbitrary linear combination of these 4 vectors, then we get an arbitrary polynomial of degree less or equal to 3, and that would be P3. How about the set that contains powers of x? Powers of x with the power non-negative powers of x. Then we get P. We can show that the span of a non-empty subset of a vector space is a subspace, and therefore is a vector space, and that was theorem 7.3. Using theorem 7.3, we can define useful vector spaces. For example, let's consider the function space f with the domain S that is an interval from 0 to 2 pi, and we define the subspace of the function space here, that is the span of these functions. 1 cosine t sine t, cosine 2t sine t, continue on to cosine nt sine nt, and continue on and on. And this is t from 0 to 2 pi is defined as the span of these trigonometric polynomials. And this subspace, also a vector space, is called the space of trigonometric polynomials.